George, you're muted for the Zoom room.
So at the end of the semester, we get everything squared off. And then the semester is over, right? That's how it goes usually. Okay, so short lecture today. Very simple concept, but very easy to get lost. So let's see if we can get everything squared off, and then we can start our weekend. Yes. We'll get some all the goods. Enjoy, right? Balance. Okay, so let's talk about effective nuclear charge. And that's the single topic for today's lecture. Okay, very good. Let's get this going. So this is a very short topic, and it's a box in the chapter 1.8, but pretty easy to get lost. Okay, so last thing we covered last time was regarding electron configuration, and I talked about the off-bowl principle. Okay, so you all know how to fill up shells and subshells to get the electron configuration. Okay? And remember, when you are filling shells and subshells, you start by the lowest energy and then move to high energy shells and subshells. Okay, so now let's think about something here. Will an electron in the 4s orbital feel the same attraction by the nucleus compared to a 1s orbital? So that's here is the first question. So use your scientist, use your knowledge and your intuition to think about that. Okay, so let's think about that. So if we have an electron in the 4s orbital, will it feel the same attraction compared to a 1s orbital? Okay, so probably not, because the 1s orbital is right there in front of the nucleus, very close, while the 4s is far. So our hypothesis then is that, okay, they will not feel the same attraction because of distance. Okay, so that's our hypothesis. So let's elaborate on the hypothesis. In science, we always like numbers, right? And calculate things. So let's see if we can find a number to quantify how much the electron fills the nucleus. And that's the concept of effective nuclear charge. The nuclear charge felt by electrons in different shells and subshells is not the same. The effective nuclear charge allows us to compare how the nucleus attracts electrons in different shells and subshells. Okay, always start with your scientific intuition, and then we will try to measure how much is the attraction. Very important point here. Higher the effective nuclear charge, the higher the attraction from the nucleus. higher the effective nuclear charge, the higher the stability of the orbital. Okay. More attraction felt by the orbital, that means the energy will decrease and this orbital will achieve stability or be more stable than one. Okay, so keep that in mind. Very important concept. Very important. Okay, very good. So we have an idea of effective nuclear charge. Now, let's see how we calculate the effective nuclear charge. Very simple formula. Effective nuclear charge represented by ZF is equal to the atomic number Z minus the Slater shielding factors represented by S. Okay, so the Slater shielding factors will change for when you are looking at S and P orbitals compared with D and F orbitals. Here's the rule. If you are analyzing the nuclear effective charge and you are looking at S and P orbitals, S is going to be equals to 0.35 for any orbital in the same shell per electron, 0.85 for any orbital in the shell in front of the one you are looking at, and the shielding factor is going to be 1 for any other orbital in any other shell. If we want to look at the nuclear effective charge under D or F orbitals, the shielding factor is going to be 0.35 for D and F orbitals in the same shell, and 1 for any other orbital in any other shell. Okay. So attention here. If there are S and P orbitals in the same shell, the shielding factor is going to be 1 for each electron.
Is that, the last one, if there are S&P overlays in the same shell, is that a separate concept or is that part of the blue size?
Part of the right side.
Okay.
Okay, so at this point, I want to go over one example with you to see how we will apply those. Okay, so let's take a look at the nuclear effective charge for a 3s electron in the sodium atom. All right, we are looking at sodium. Atomic number is 11. And the question here is to determine the Z effective for the 3s orbital. All right, when we have this sort of problem, the first step is to write the electron configuration. So we are going to fill shells and subshells. So starting with 1s2. Next one is the 2s2, 2p6, and finally 3s1. And we are going to look at the very last orbital. So that's the very first step where everything starts. The second step is to arrange the orbitals in an horizontal form. When I say horizontal form, I'm telling about something like that, okay? So we are going to put all the shells in a horizontal form, starting from the the shell number 1, and going all the way to the shell number 7 if we have electrons there. Okay? And let's get here a convention. We are going to use S, P, D, and F in that order. Okay, so here is a small system, but let's do the arrangement in a horizontal form. Okay, so we have the nucleus right here. So 11 positive charges. Very first shell is the 1s2, followed by 2s2, 2p6, and finally 3s1. Okay, when you arrange in the horizontal form, can you see that in front of the 3s orbital, you have 1s2, 2s2, and 2p6? And those orbitals are going to shield the charge from the loops, okay? Okay, so very good. So now let's determine the effective nuclear charge felt by the 3s orbital. First term in the equation is the atomic number. In this case, 11 minus okay, so one important thing here, we are looking at this orbital in the third shell. So therefore, The second shell is the n minus 1. And the first one is n minus 2. All right. Now we have to attribute Slater factors for each electron. So let's go back to the rules, starting with the 1s2 orbital. And then let's see here. For electrons in any other shell that's not the same and the one right in front of, the Slater shielding factor is going to be a unit for each electron. Okay? So we are looking at the third shell. The second shell is the one right in front of it. And everything after that is going to shield with 1 unit for each electron. We have 2 here. Each one shields with a unit. Okay, so that's how we are going to start building this Slater factor. After the 1s2, we have 2s2 and 2p6. And that's the shell right in front of the one we are looking at. In other words, is the n minus 1 shell. And in this case, each electron will shield with a factor of 0.85. So therefore, we are going to add the number of electrons times the shielding factor. Okay. So let's mark this here. This is the number of electrons times the shielding factor. Okay, now look at the third shell. Is there any other electron there that's going to shield the charge of the nucleus? Just one, so we don't have to count anything because that's the one we are looking at, okay? Therefore, the effective nuclear charge under the 3s orbital is going to be 2.2. Okay, so therefore, the valence electron, the very last one for the sodium, is going to feel only a 2.2 positive charge from the 11 that the atom started with. And that's why the valence electrons are the reactive, because they have lower effective nuclear charge. They are less bonded to the nucleus. Yes, sir. Can you make me a favor? Yeah. Can you take a picture of the Thank you. Okay, so Determining the nuclear effective charge is not a complicated formula. However, you have to pay attention on the shading factors that are going to be used. So let's see if I can show you lots of cases here to give you a broad idea about the calculation. Okay. So now I want to move to magnesium. Okay. And I want to determine the effective nuclear charge for a 3s electron in the magnesium. Okay, let's think about that for a couple minutes, and then I will solve the problem with you. All right, let me set up the problem. All right, we are looking now at magnesium. Z is 12, and we want to determine the effective nuclear charge felt by a 3s orbital. First step is to write the electron configuration. So 1s2, 2s2, 2 is 6, 3s2. Right? Yes.
So are we talking about all the electrons in that 3s2 orbital or just one?
That's a very good question. Always one.
Okay.
Okay, always one. Okay, so now that we have the electron configuration, we will arrange in a sort of a linear order here the orbitals. So we have here the nucleus with a 12 plus charge right in front of the nucleus. 1s2. After that, 2s2 and 2p6. And then here is the detail, and that will answer the question. We have 2 electrons in the 3s orbital, but we are looking at the nuclear effective charge under just 1. So what I'm going to do here, just to be a better example, is to do this 3s1, 3s1, okay? And we are going to look at the very last electron. So this here came from 3s2. And we are looking at the nuclear effective charge from at the very last one electron. Okay, so if you got all the way to this point, that's half of the problem. The next half is to correctly attribute the Slater shielding factors. Okay. So Z effective for the 3s orbital is going to be nuclear charge 12 minus. So here we have n minus 1, and n minus 2. 2 electrons are going to shield with a factor of 1, all right? Plus 8 electrons shielding with a factor of 0.85, because that's the shell immediately in front of the one we are calculating. And in this case, we have 1 electron in the same shell. And the shielding factor when you have electrons in the same shell is 0.35. Okay? So always count everything that is in front of the orbital you are looking at. Therefore, Z effective for the 3s orbital in the magnesium is, according to my numbers, 2.85.
The effective charge.
That's how much positive charge that orbital is feeling.
Okay.
Okay? So from the 12 that started with, to get all the way to the very last orbital, you are left with 2.85 positive charges.
Okay. Are those numbers experimental or mathematical?
That's completely mathematical. Okay? So it's, you can compare things with the Z effect. So it's not an absolute kind of thing.
Okay.
So we are just makes sense to compare numbers.
Sure.
Okay?
Professor?
Yes.
So the Z effective is a way to kind of measure how easily or how readily an atom will give up an electron.
Exactly.
Okay.
Exactly. How strong is the attraction by neutrons, in other words, okay? Okay, so very interesting thing here. Let's look at the 3s for the sodium, 2.2, okay? And the 3s for the magnesium, 2.85. If you look at the periodic table, magnesium is right after the sodium in the same line, in the same row. The only difference between sodium and magnesium is 1 proton and 1 electron. Okay? From 11 to 12, you added 1 proton and also added 1 electron. However, which element will attract with a higher intensity the valence electron? Sodium or magnesium? Magnesium, because the Z effective is large. Let's think about one thing. If magnesium attracts with a higher intensity the last electron, what should happen with the size of magnesium compared to sodium? Smaller or larger?
It should be smaller.
Smaller because the attraction is stronger, right? Therefore, when you move across a period in the periodic table, what should happen with the size? Shrink. Shrink. That's what we are seeing here, right? You are adding protons and electrons, but the electrons are always in the same shell. That will increase the Z effect. So when you move up and down, you are adding extra shells, therefore the size will get larger. So therefore, using the Z effective, we figured out what should happen with radius across a tube. Okay? Now you know the reason. And that's the difference between you and a freshman student. You know why. They accept things. You have to know why. That's your mission. So when you know why you don't accept things, you can argue. Right? And that's another level. It's true, isn't it?
Yeah. No, you've done.
You know, so imagine knowledge as a sphere. More knowledge you have, larger is the sphere. But the surface of the sphere is all your questions. So larger the sphere, larger the surface, so more questions.
Does that mean it's also easier to lose information that you've collected?
Absolutely, right? It's hard to keep track of everything. I mean, you know, the information is always there. Sometimes you have to recap. But once you start recapping, then it comes. You know, now that we have internet, we have a lot of information, but is it correct or not? Exactly. So you've got to be able to differentiate, or at least, okay, this makes sense. Not saying anything about your age, but remember the dial-up internet.
Yeah, so you had to be serious. You had to know what you were looking for.
I know, right? And my mom only allowed to use after midnight because it was cheaper. Yeah, in the dial-up, when you connected, you were using the telephone. It was like you were making a call, right? And after the midnight, no matter how long the call, it only counted for one phone call, like 1 minute or something like that. Yeah. So everybody tried to connect after midnight, and the server couldn't handle. And the speed was what, 25 kbps.
I was just so happy when we got like 9,600.
Yes. Oh, it changed so much. Changed so much. in floppy disks, with like 1.2 megabytes, something like that.
Yeah, we would run companies on a 10 megabyte.
Yep, yep. I remember my first flash disk, I still have it. It was 52 megabytes. And that was top of the line. And like this big, this big. Still have in my office. Anyway. Okay, so to wrap up for today, and your horse is over there. Let's talk about the case of potassium, the potassium electron configuration. And I want to show you how we can use Z effective to figure out where the electron should go in any configuration. Okay, so let's take a look at potassium. Atomic number 19. And the first thing I want to do here is to draw the electron configuration. So we are going to go 1s2, 2s2, 2p6, 3s2, 3p6. So I guarantee you that if we go to the CHEM310 class, 50% of the class will draw the next electron going to the 3d1 orbital. This is right next, right? However, we know that it has to go to the 4s1 orbital. So what I want to do here is to do a quick calculation of the Z effective, looking at the very last orbital, considering this configuration and this configuration over here. Let's see which configuration will have the highest Z effective. And then we will decide which one is the most stable. Yes.
Is it also going to show the trend going down?
Kind of. It will help a little bit, but doesn't get too accurate, actually. And there is another effect that I will show you instead. Okay, so when we have d orbitals or f orbitals, it gets tricky with the rule, and it's very easy to misunderstand it. So here is what we are going to use for the later shading factors. 0.35 if we have d and f orbitals in the same shell. Okay? And any other orbital in the same or another shell will have a Slater shielding factor of 1 unit. Okay, so see the difference here. If we are looking at shielding over 3D orbitals, S is going to be 0.35 for each D and F electrons in the same shell and one for any other orbital in any other shell. So I want to do the 3D run example with you, just to make sure we get this right. So Z effective for the 3D orbital is going to be 19 minus. We are looking at the 3D orbital. Is there any other D or F electron in the same shell? No. So therefore, everything will have a shading factor of 1 unit. Okay? So therefore, 2 times 1 plus 8 times 1 plus 8 times 1. That will give us a Z effective of, according to my numbers, 1.0. So now we are going to do, again, the Z effective. However, we are going to consider that the electron goes to the 4s1 orbital. Okay? All right. Let's remove this here. Now we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. This is n minus 1, n minus 2, n minus 2. Okay, so now we are looking at an s orbital. So therefore, we are going to use the rules in red. Z effective for the 4s orbital, 19 minus 1s2 orbital will have a factor of 1, 2 times 1, plus second shell, also a factor of 1, plus n minus 1 shell, 0.5, and that's it. Therefore, the Z effective for the 4s orbital, according to my numbers, is 2.2. All right. Which orbital has the higher Z effective? 4s. Higher Z effective means higher stability, okay, more attractive. Therefore, the 4s1 configuration is more stable than the 3d1 configuration. And that's why the electron goes to the 4s orbital and not to the 3d orbital. Okay. All right, so this sort of calculation requires a lot of practice. So I will make some exercises and post on Canvas, and then you can practice calculating this effectively. So make sure you have the rules in your head. Consider everything that it is in front of your total. Okay, so now it's a good time to finish.
I have a question.
Yes.
I've never seen electron configuration stacked up like that. I've normally seen it in a row.
Doesn't matter. I like to stack because I go in the diagonals. If you get the same thing, doesn't matter. Okay.
I like it better actually in a weird way.
I think you don't get lost this way,
Yeah.
especially when you get like larger configurations, but it's up to you. You need to get to the same reason. All right, guys, thank you very much.